So then let's continue from yesterday. The last thing that we got to do was to talk about veil divisors on normal varieties, and we pointed out that with a little bit more of commutative algebra, you can remove this assumption for the definitions below, but let's add normality to make things easier for us, since we have normality anyway for the toric varieties that we want to consider. So then I remind you that we are going to say that an irreducible divisor, by that we mean use a sub-variety of the normal variety where we are working that has codimension 1. So if we had P2, this would be just like some irreducible curve. Those are the irreducible divisors. And now take formal combinations with integer coefficients of those. So it's the free abelian group generated by the irreducible divisors. Those are the ones that we call veil divisors. Very good. And I remind you that if you have a rational function in your variety that is non-zero, with normality, we get an easy way to define the order of vanishing or the order of zero or whole of that function f along any codimension 1 subvariety. We just use that the local ring is a DVR in that case, and then we use that valuation to produce like a positive number that is the order of vanishing or a negative number that would be the order of the pole. And then we can produce a divisor by taking order of the polar zero or pole along each codimension 1 subvariety for your f. Then as we pointed out, this is a finite sum because you can, given that f is non-zero, is regular and some open, and then on a possibly smaller open, 1 over f is also regular, and then you have that over there is invertible, and on the only divisors that could contribute to this sum would be the ones containing the complement. Because if you are contained, if you intersect this open that I said where f and f inverse are regular, then this number comes out to be 0 because it's greater or equal than 0 and it's smaller than or equal than 0, applying it to f and 1 over f. So then again, this sum is finite because it can only be non-zero on divisors that are containing the complement of an open, which is some closed set, and you will have finitely many components. Very good. We also said that linearly equivalent divisors are those that differ by one of these divisors, which we call principal divisors. So then again, principal divisors are the ones of the form div f. For f, a non-zero rational function, so f is a regular function on some open set of x. We take this formula and get a divisor. The ones of that form are called principal divisors, and two that differ by a principal divisor are called linearly equivalent. And then the class group that here on these notes we are calling the Chow group of dimension n-1 of index n-1 would be modding out our divisors, our veil divisors, by linear equivalence. So we have the Chow group over here, and now we are going to look at the toric case of this picture that we just reviewed. Okay, what about the case on toric varieties? We claim that we can compute these guys. Let's see. So looking back at what we learned about orbits, we said, okay, you have your toric variety. It comes from a fan. That fan is a collection of cones. And we said the orbits for the action of the torus on the variety correspond to the cones. And moreover, we say that they fit basically in the same way. Like the orbits are different, but if I take closure, a smaller cone has a closure that fits cones that are bigger than that one, that contain it. Okay. And we also said that if we have these closures, these orbits, and then we take the closures have the same dimension. And then we also said that the dimension of the cone plus the dimension of the corresponding orbit, or equivalently of the corresponding orbit closure, those add to n, to the dimension of our variety. Then in particular is that it says over here, if you have a one-dimensional cone, which remember we have been calling those rays, those guys correspond to an orbit that, an orbit closure that has dimension 1 less than n, because plus 1 adds to the total. So it's codimension 1. Okay, that's what we are calling a divisor. So the rays are corresponding to the invariant divisors on your variety. Let's use this notation over here. Let me show you which one. This is going to be the set of all rays in your fan. And then those are in correspondence to the divisors that are invariant. And to clarify, we don't mean that it is point-wise invariant. It's invariant as a set. So if you consider this codimension 1 subvariety, and it is the action of the torus sends each point in that divisor to another point inside that same divisor. That's what we are defining to be an invariant subvariety in general. Then it's not necessarily fixed point-wise, but it's fixed as a set by the action. And those, just by what we learned about orbits, are in correspondence with our rays. Now, just also analyzing the correspondence between orbits and cones and how they fit together, we can see that our toric variety looks like this. You have your torus, and the complement of that is precisely the union of the invariant divisors. So it looks like this. Your X, if this is X, and this is the open set that is the torus, and you look at the complement, this complement would look like this. Would be the invariant divisors over there. Then again, what I'm saying is, if I take the union of these invariant divisors with the open set that is the torus, you get your toric variety. How do you see that? Look at what the orbits are. We know the orbits are in correspondence with the cones. And then I need to make sure that if I want to really check that I get all of the toric variety, I just need to make sure that I get every single orbit, but I do. Because the orbit corresponding to the zero cone is over here, and the orbit corresponding to any other cone is dimension 1 or more, so it contains at least one ray. And then looking at the correspondence between orbit closures and cones, I see that then it will be inside the divisor corresponding to that particular one-dimensional cone, to the particular ray, so it is in one of these ones. So then we are not lying over here. And then notation will be as follows. Sometimes we are going to want to take some union over all the rays. We are going to denote it like this. I'm sorry. This is better. So if we are going to take a union over the rays, we will write this. If you want to take a summation over all the rays, we want to write this, and so on. Again, that would be for operations done over all the cones of dimension 1 in your variety, which again we call rays. Okay. Now, there is a nice relation between the characters and divisors. We are going to see something about this just next. So the way that it is written here is that this guy is a map from here to here. So I can consider it as a regular function there. But also there is a different way to think about this. Just T. T is, in this notation that we were using, spec of M. So a spec of C of M, of the semigroup algebra associated to M. Then the coordinate ring of the torus is just C of M. Then chi to the u is in the coordinate ring, so it gives me a regular function in the torus. But if you have, let me write down this. if you have U in M is this lattice, so minus U is also in M. So U is giving us this function from here, from the torus to C star, well, in principle to C, depending on how you are thinking about this, it's in principle to C. If you are thinking of it as a character, I already know it's to C star. But if I'm thinking of it just as a regular function, coming from the spec part, I get that it goes to C, but then minus this other one is also there to C. And then I deduce that, okay, both actually go to C star. Depending on your point of view, it comes for free, or you need a tiny argument to C. Since you also have minus U, then that gives me an inverse. So it actually lands in C star. Anyway, what I'm saying here is that since T is this affine variety corresponding to this guy, then this is the coordinate ring. This guy is the coordinate ring. This is what I mean. This guy is the coordinate ring. So a function for here is for free regular on the torus. Okay. Then now what is our situation? We can ask for the order of vanishing of this one along any divisor in the torus, or we can also ask for the divisor associated to this thing. And this one gives me something T invariant, one can see. So this one, if you act with the torus, what happens is that, well, let me just say this. This one is invertible in the torus. So if I take the associated divisor, first, since it is regular, when I go and look at my local DVRs over there, I always get greater or equal than 0. So the divisor associated to this regular function in any event has coefficients greater or equal than 0. But I can see that the divisor for chi to the minus m is just minus the divisor associated to this one. And it's also, this function would also be regular. Chi to the minus m is also regular. So the divisor associated to this guy has coefficients greater or equal than 0, and the divisor and minus that one has coefficients greater or equal than 0. Okay, so it's 0. So then, what am I saying? This guy gets 0 order on all divisors in the torus. Going back to my picture, I have on X the divisors out here, the invariant ones, and I have like a lot, like a crazy collection of non-invariant ones, things like this. And we just said that if I take chi to the u and I look at the order of chi to the u on all of these purple ones, I get 0. So going back one slide, if I apply this formula to chi to the u, I get non-zero in these coefficients only in the invariant ones outside. Again, it's because chi to the u and chi to the minus u are regular on the torus. So when I apply the formula, I get 0 coefficient over there. Okay, so then it means that the divisor div chi to the u, as it said here, is supported on the red ones in this picture. Is supported on the union of the invariant divisors. That's what we are saying. If we do div of chi to the u, is going to be some sum of a row, the row for row in the race of the fan. So it's going to look like that. But our task is to figure out these numbers. And then we can say, okay, what are those guys? Well, the point is that is at the order of vanishing along something, which I can do by going to the local ring of that one. So I can pass to any neighborhood that intersects one of these D rows. So if I want to compute the coefficient of this for a particular for a particular D row, if I want to compute a row, I can pass to any neighborhood, any open set in the variety non-empty that intersects the row. And then there is a very natural choice. Let me look for a little bit of a space and draw it over here. You have a fan, possibly with a lot of cones over there, and then you can have like a lot of cones over here and so on. And then if your ray rho, say, is this one, this is rho, what would give us an open set that intersects the corresponding rho? The following. I'm going to take only two cones. I'm going to take, but basically it's just the V rho from before, the affine V rho from before, which I get by taking basically these two cones. Although when I write V rho, it's already there, but I can think of this fan. Think of the fan that has only two cones, rho and 0. That gives you this V rho. It's an open set inside your X sigma, and by the correspondence between orbits and cones, it intersects the rho. So I can compute this order of vanishing there. One of the reasons for which this is good is we don't need to use any of the outside, and now I can change coordinates. I can change coordinates so that this ray, is anything I like. For example, I can change coordinates so that the ray is now this guy. And now this order of vanishing over there is basically when you take the dual, you go to the dual picture, the dual cone would be this over here. An order of vanishing you can compute by looking at lines like this, and then you see this dot product with this vector over here will read order of vanishing for you. Although this step is not really needed, I didn't need to change coordinates. I could have done the same thing without changing coordinates by looking at lines like this. Take dual first, and then look that you compute order of vanishing. Now it's an easy local exercise just by doing dot product with the vector over here. But it's easier to see if I change coordinate. Because, for example, for this picture, what does it mean? I have like an x over here. This would be like the ones that is x squared something, x cubed something, and something. So to see order of vanishing, I see how deep you go toward the right. And then I detect how deep I am just by doing dot product with this vector. What are we really saying? That this is what you get. That passing to a very convenient neighborhood that intersects the rho, this is the coefficient that I was calling A rho in the previous slide. That coefficient is exactly computed by doing dot product with the first element of the array. I remind you, we have this notation. If we have a fan, lots of cones over there, and say that there is this cone rho, you intersect with the lattice, so you get something looking like this. The integral points in that ray, there is a very first one. That very first one we call V sub rho. And the argument I outlined shows that the order of vanishing of any of these functions chi to the u along the particular codimension ones of variety corresponding to the array is computed simply by a dot product. Dot product of the only things on site. Dot product of the m, that gives me my character, and of the v rho, that is the first lattice point on the array. Then that tells me, putting these coefficients together, that we have the principal divisor associated to chi to the m. We already said that it's invariant, so it's just a sum of the invariant divisors with some coefficients, and we computed them above. Those are the coefficients. Excellent. So it's a very good start. We now know the principal divisors associated to the functions of that form, but those are not all of them. There are div f's for f's that are not invariant at all. So we need to deal with those in a moment. So this is what is going to happen. there is this sequence. There is a very easy exact sequence to compute this. So I remind you, this subsection that we are discussing right now is to get this object that maybe some might be more familiar with the notation, the class group. We are saying we get a direct, very easy computation of this for toric varieties. What is the computation? You take the direct sum of z times these guys. What are we saying over here? It's all the invariant Veil divisors. All the Veil divisors that use only invariants of varieties as irreducible divisors. And then we just use principal divisors that arise of this form. Given u in m, well, I'm going to match the notation above. Given m in m, send that m in m, send it to div of chi to the u. That's what this map does. And then the claim is that the co-kernel of this simple map computes for you this child group or class group, if you like to call it that. Yes, please. You are right. Thank you. I changed notation, but only in some places, not everywhere. Thanks a lot for pointing this out. Thank you. But very good. Let's say a word of why this is true. So I can tell you a word. What is this object that we really want? Well, we want. This object is, we take any formal combination of codimension ones of varieties. So in a picture over here, we have the torus, and we have this here, x sigma, the torus, and if you are given one element here, take a representative. That set was defined as, you take formal combinations of codimension ones of varieties, and you mod out by div of f, all the div of f's. So all principal ones. So, yes, please.
I remember the definition of shell group
Yes.
is by algebraic equivalence. In this case,
it's the same. In this case, it's the same. Yes, very good. It's an excellent point. In this case, it's exactly the same. Like that, and n-1, I can present it like that. In the other ones, I need to do a little bit more. I take some varieties inside your variety, and then you normalize, and then you do div of something there, and then you do the push forward of the cycle. It requires a little bit more work, but in this case, you see it's exactly this. Thanks a lot for pointing that out. Yes, like when one does like some algebraic equivalence for this one, but in this case turns out to be exactly the same. Yeah, very good. We are not cheating. Those are literally equal with the usual definition. Thanks a lot.
But in this case, you mean that
n-1
is normal, right?
I did those. I would get like this with n-1. Yeah, I have to think. In normality, for sure. In normality, for sure.
But then maybe if that sigma is not normal, this is not going to be the Picard group. Or...
If it is not smooth, this is not the Picard group. Yeah, if it might not be the Picard group. Yes. If x delta, x sigma is not smooth, then this guy is just doing these divisors that are Veil divisors modulo equivalence, but the Picard one would be only looking at the ones that are locally principal. Because for the Picard one, you will be looking like line bundles, so those ones are locally principal. So yes, like if it is not smooth, this you will not have the Picard here. If it is smooth, you could put here the Picard group.
So then I have to check the factorial.
But I'm not putting the Picard there anyway. So I don't need to deal with smoothness or not here. Very good. So the representative would look like this and like this, right? So a representative, if I take a particular d bar over here, then D, the representative, has some components that intersect the torus and has some components that do not intersect the torus. But then this is what happens. The coordinate ring of this one is C of M, which is a localization there of the polynomial ring in one variable. So then one can see the polynomial ring in one, not in one variable, in several variables, is a UFD. Then you see that this C of M is a UFD. And then when you have spec of a UFD, that one has a trivial class group. It's easy to see because unique factorization gives you that the height 1 primes are principal. But then those height 1 primes correspond to these varieties. Then I can make each one of these principal, and then putting those equations together at the appropriate power coming from the coefficients, I get that this part is on the torus, there exists an F T star T of X, rational function non-zero, such that if I do diff of that F and I restrict only to the torus, it gives me the blue ones. And the reason is that C of M is a UFD. So then the height 1 primes are principal, and then I'm able to get that F. But then that means the following. If I do D minus this, D minus diff of F, it removes all the blue, you see? So D is linearly equivalent to D minus diff of F, and that one now is supported on the complement of the torus. And this one is supported on X minus the torus. So it's now which is the union of these D rows. You see, we were able to, given any cycle, like any of these divisors, we were able to find an equivalent one just done by invariance. And again, the key point was that over the torus, I have a spec of a UFD. The coordinate ring is a UFD. I can do that always when we have that. The class group in that case is trivial, meaning this, that I can find always an F, that when I do diff, I get what I want. So every divisor like this is principal. But then what we just said is that this map is surjective. You see, everyone here is represented by one divisor. This map beta is taking class. You have a divisor, it has a class in this class group or child group. Then what we are saying, hey, these guys come from formal combinations of arbitrary codimension ones of varieties. The fact that this guy is a UFD allowed us to have a surjection with a very special type of codimension ones of variety. And now one can take a moment to see that the kernel is the ones among these that are principal. And then you ask yourself, which Fs can give me a diff F supported just only on the invariant ones? Well, the first thing that you realize is that it has to be regular on the torus, because otherwise it will give you other things that are not, it will give you other components here that don't look like this. And also the inverse is regular on the torus. Then you get that is one of these, well, you have a regular function on the torus, so it's in the C of M, and then by the invariance. It's an easy exercise now to check that it's not just an element of C of M, but it cannot be a sum of several chi to the u's with coefficients. You will break the invariance. It's easy to see. So it actually simply looks like if one of these is principal, is diff of F, but F actually has to be a chi to the u. So that means that the kernel is this guy. So we outline what this sequence, why this sequence is exact. But the point is, hey, if you want the class group of a toric variety, there is this exact sequence, very simple, that computes it for you. Then let's say a word in this case. Well, before we move on, let's point out that in some cases, you can add a 0 here. When? Well, let's just look at what the map is, and then we deduce it ourselves. Maybe I can do the following. Select that page, and then copy it, done, and then insert it over there at page A before, that one, and then close here, and then go to this one that is empty, and then point out what the map is so that we see when it is injective. When would this be injective? Well, it does the following. It takes M into this thing by a bunch of components, but they look like this. If I write them horizontally, is M dot product of, say, V row 1, comma, M dot product with V row 2, M dot product with V row R, if there are R arrays. And when would this be 0? Well, it would be that M does dot product with the first generators of the arrays, dot product 0 with those guys. Then, for example, just put this over here. If you want all of those 0, then if the arrays span in R, meaning like if you have one of these complete lattices, for example, although that's not the only case in which it happens, but say that my arrays look like this, and these guys, even I didn't need so many, but like let's see, they have these guys. These 4 vectors span the whole vector space. So in that case, any vector that does dot product with these vectors, does dot product 0 with those vectors, does dot product 0 with the span of those vectors. So it would be a vector in Rn that does dot product 0 with the whole Rn. That's only 0. Then it would mean that this is injective. Very good. So then this is what is pointed out here. If you have that the arrays span in R, then I can add this one part here. Yes?
In case that this condition is not true, can I not just like take the fan and it's not going to be of maximal dimension, so there's like a subspace containing it, and then replace n with that subspace and get an exact?
Yes. Yes, you are right. Yeah, if these guys don't span the whole thing, my fan would leave in something smaller dimension. And then when you do that, you can basically pass to the quotient, and what you end up with it is just like for example, when you have just 0, say that your fan was just 0, and you get the torus. What happens in that case is that you just get a product by a couple of copies of C star. Like what happens when, for example, the extreme case of what you said, your fan is just the cone 0. Then you get the torus at the end. What I'm saying is that if you had like a fan that generates like the span of all the arrays is a smaller dimensional subspace, you can pass and work only in that one smaller dimensional subspace. You get a toric variety just out of that picture, and the one that you would get in the original space is some number of C stars equal to the difference of the dimensions of these two cross the toric variety that you get in this smaller subspace. It's easy to show.
So it's not the same.
Because the toric variety that you end up with has the exact same dimension as the lattice. So if you choose to pass from the big N to an N in a subspace, the variety that you get now is smaller dimensional. And how does it differ from the one in the original one? It's just by a product with a number of copies of C star equal to the difference of the 2 dimensions. Like extreme case, this is the one that I said, that you take the only cone is 0, then you get something trivial cross number of copies of C star to the dimension. So you get the torus. Very good. So let's now see some examples using previous examples that we did. We have written the fan for P1 cross P1. So we said that it looks like this. Let me go over here. we use E1 minus E1, E2 minus E2, and we end up with cones that look like this. The two-dimensional ones look like this. Then giving names to these guys like V sub i's, let's take them in some order, which the order does not really matter, but we choose an order for simplicity. See that we call this one V1, this one is V2, and this one is V3, and this one is V4. Yeah, I got them in the correct order here. Very good. Let's each one of these rays, like the VI's are the first lattice vector along the ray. Each one of those rays gives us an invariant divisor. Then let's write this part of the sequence, and this part here computes the class group just as the kernel. This one here would be the class group of our P1 plus P1. But say that we don't know yet. What we're looking at is this part of the sequence. So what goes in this part is just Z times this guy plus Z times this guy plus Z times this guy plus Z times this guy. Here goes our M, which in this case is Z2, is the dual lattice to the lattice of this one. So this one is a Z2. The dual of Z2 is Z2. So we put Z2 here. And I remind you, the map, alpha over here, we get in each entry, it has 4 components, and the 4 components are dot product with the V's of i's. So the first component is dot product of this guy. Well, a vector A comma B dot product with this gives you A. Dot product with this guy for a vector A comma B gives minus A. Dot product with this guy with for a vector AB gives B. And dot product with this last guy over here with a vector A comma B gives minus B. So the 4 components that I put over here, we have them here, A minus A, B minus B. What I'm saying is we know what the map alpha is dot product with these vectors. And then dot product with those, and those are the 4 components, but it's a direct sum over there, but here we're writing it as just as an element over here. Very good. So we have the map alpha very explicit, and now one can just see what the co-kernel of that is. And then you can see that this completes the picture. This one, it gives you a Z2 as a quotient, is precisely the co-kernel. So that we have computed that this class group is Z2. Very good. I mean, there are other ways to do this, but we just picked a relatively accessible example so we could see how it works. Very good. Let's take another one that we have said what the fun is before. Weighted projective space. Before we said that the lattice that we use is Zn plus 1 mod out these guys, this vector, the multiples of that vector. Because what we want, if we didn't mod out, I can tell you something that may help intuition. Something that people do is that instead of starting, like, let me go to the case of projective space. Some people like to say, okay, you take the vectors E sub i's, E sub 1 to E sub n, and you add a new vector that is E0 that is minus the sum of the EI's. So you have chosen coordinates in a certain sense. Some people like them to start with Zn plus 1 and then mod out by a copy of Z, having the bases at 2, 0. To try to produce a coordinate-free way. Like then for weighted projective space, some people might like to start like this. Say that you start with vectors V sub 1, V sub 2, and so on. Actually, let's start from V sub 0, V sub 1 up to V sub n, that they are primitive, meaning they are not the multiple of some other integral vector. They are primitive and lattice vectors. They generate Zn, which is not for free, and additionally, they satisfy the relation that we imposed below. They satisfy that Q0, V0, this is the last condition that we are adding over here, plus Qn, Vn equals 0. Take vectors like that, and now ask, get a fan out of them by taking all proper cones spanned by any proper subset of this collection. It gives you weighted projective space. Then over here is the same, but done in a coordinate-free way. Well, slightly more coordinate-free than this. So you start from here and impose this relation. It's essentially the same. Now, let's do something. We have a short exact sequence for this guy, right? We have the sequence that goes like 0, Z included in Zn plus 1 by like product with this Q0 to Qn over here, and then the quotient Zn plus 1 mod Z times that vector, 0. Then take the dual of this one. What do we get? Well, this one over here we want to consider because it is our n, right? That one, this one is our n. So when we take dual to this sequence, this m is here. You could think like, oh, we run into trouble, but no, like with some type of exactness, but not really, because this guy is projective, this guy is a lattice. So then I don't have trouble if I take this home, I stay exact. Then my situation now is that this map over here is going to be given by dot product with this, because I understand the one above, and then I get to identify my m with the kernel of that. So I get this sequence over here. Let me color it with some other color, but we get this sequence. Let me erase a little bit. We get this sequence. What is that sequence? This one is the inclusion of the perp of this vector in Zn plus 1. So are the elements of Zn plus 1 that give you dot product 0 with this guy, with this vector, and over here the map is dot product with these ones. So we have this exact sequence, and then it takes a moment to realize that when you identify this one with this other copy of Zn plus 1, the diagram would commute, like the diagram that is M going to this sum of Z di over here like this, and over here, down here, the map was taking div, that map commutes. So what I get over here is the exact same kernel that I will get, co-kernel that I get from the one below. So this one is computing for us this class group of weighted projective space. So then what is the answer? That this an minus 1 of this p q0 to qn is isomorphic to z, or equal to z if you like. And where do our di's go? That's important. One can think for a second, and this one in the middle is this sum, and the map is dot product with these qi's. So if you take the sub 1, it's like having the canonical vector 1 0 0 0 0 0 0, then dot product with this recovers q0. Then let me say that answer. The answer is then, okay, if you have weighted projective space, you have a fan that is very simple, is n-dimensional, has exactly n plus 1 rays. The cones are all proper, spanned by all proper subsets of that. I have n plus 1 rays, so there are exactly n plus 1 rays, so there are exactly n plus 1 invariant divisors. The class group is Z, and I know the class of each of them. You're going to be an integer. Which integer is it? For the first one is Q0. The first one is like degree Q0, degree Q1, and degree Qn. That's the answer that we get, and we see it from here because it's each di corresponds to the canonical vector is of I. Do dot product with this vector, you get Qi. That's a result that is very useful for me, I guess. And now let's talk about this one that in the notes, I believe is called a homogeneous coordinate ring. But then I think that name is a bit confusing because there are other things with that name. So more recently actually has been called total coordinate ring and also Cox ring. But maybe since we are using some notes of David Cox, we didn't want to put his own name over there. But I think the most common name seems to me to be the last one over here, the Cox ring. Then, and it's going to allow us to get our variety out of a quotient construction. So let's go and take a look at this situation. We mentioned that in addition to the first construction that we gave of a toric variety out of a cone, affine ones out of cones and abstract ones out of fans, that produces all of them, all the normal ones. We mentioned that there are at least 2 more ways, and we were going to briefly discuss those. This one is one of those 2. So we are going to produce a ring out of the variety, and we are going to say how to take a quotient to recover the variety. And this type of thing is nowadays exists not just for toric varieties, but also for something called Morley-Dream spaces. And let's look at, it used to be called homogeneous coordinate ring, and then that's why the notes call these homogeneous coordinates. Then even if you change the name to this or this, I guess you would still call this type of things homogeneous coordinates. So let's look at the example of Pn for a second. Pn, we can consider in that case, the one with the actual name homogeneous coordinate ring is this. And then there is an affine space associated to that. The affine space associated to that one is Cn plus 1. There is a notion of an irrelevant ideal over there. And there is this set 0 that when you remove it and you quotient by C star, you recover your Pn. But then one can think for a second of what 0 is and what C star is, what role do they play in the picture, and can generalize this. So let's see how it can be generalized. Let's start from a toric variety, X sigma. So sigma is a collection of cones. Out of those cones, you get an affine variety, and the collection of cones, when one is a face of another one, the corresponding affine varieties, one fits in the other one as an open. So you use that to glue them and get the X sigma. Okay, so we are an X sigma glued out of some affine opens that are toric varieties coming from cones. Then, let's construct a ring out of the data of the fan. It is just a polynomial ring in this case. If you want to generalize to these ones called Morley-Dream spaces, it's no longer a polynomial ring in general, but here it is. So we start with a polynomial ring in as many variables as the rays, as the number of rays. So for example, for P2 that looked in the toric picture like this, like the fan looked like that, you start from a polynomial ring in 3 variables. For this was for P2. For P1 cross P1, we mentioned that the fan looks like this. The number of rays is 4 in that case. The number of one-dimensional cones is 4. So we will start with a polynomial ring in 4 variables. But we don't want just that. It's not just the polynomial ring. The important thing is the grading that we are going to give to it. we are going to grade it by the class group, or in the language that we are using here, we are grading it by this. And as follows, we are going to use the following notation. We are going to think of this particular monomial. So you let rho vary over the rays. For example, in this case, it varies over these 3. Here it varies over these 4. That's in correspondence with the variables. So it's just the variables to some exponents that are integers greater or equal than 0. So that, in my mind, I make correspond to this divisor. I just simply take this as the coefficients, and I use the row to decide which the row to write over there. So I can pass between these two just using the notation that I see. I see an row here, put it here. Okay. Then now we are going to give a degree to each of the x rows, but not generally products of them. If you have this monomial, write it informally as x to the d, where d is this. The degree of this guy, the degree of the monomial, is the class in the class group of that divisor d. Ideally, one can say that maybe in a slightly less complicated way. The degree of a monomial that is a product, say, x. Let me pretend that I have R of them and was to look like this. I'm going to remove the row from the notation to try to make it look a bit friendlier. This degree would be the class in the class group of the following divisor. You take A1 D1 plus A2 D2 plus AR DR, whatever the class of that is in the CLX, which is n AN minus 1. Very good. So that is the grading that we are giving to this one over here. Let me. Yes, please.
That index down there, that row, that runs over all rows in sigma 1, just in the notes that's written. Note that a monomial.
Could you please see which part you are?
Yeah, just the very first line.
The very first line. This one? Oops.
I guess let me rephrase my question. What's the degree of just one x sub row?
Very good. The degree.
I'm not sure it's clear from this definition.
Yes. So the degree of one x sub row would be the class in the class group of this guy. Yeah. Like, yes, you have a monomial, but each variable corresponds to an invariant divisor. Each x sub row corresponds to a d row. So use the exponent that you see as a coefficient to form a divisor. And then it makes sense to ask what is the class of that divisor, and that's the degree. So this again is well studied and is called the Cox ring of the variety. And one can define this object beyond toric varieties. Okay. Then this ring with the grading that we gave it is called the total coordinate ring, but I guess most people use this name, the Cox ring of the variety. Then let's look at a quick example using the ones that we have been using for the previous claims. P1 cross P1, we have said that the fan looks like this, with cones over here, over here, over here. Those are the maximal ones, and now is the faces of those guys. We have 4 rays over there, and using the same order that we gave before, this one was like the first, this one was like the second, this one up here was the third, and this one over here was the fourth. Then now let's take a look. Again, this means that inside the variety, there is an irreducible subvariety that is fixed as a set under the torus action. I just write it over here because there is a correspondence between the cones and those invariant varieties. So this D sub 3 does not live there. This is a picture living in R2. So then again, it is informally written as D3 here because it corresponds to this particular ray. Very good. So there are 4 rays. Then we start with a polynomial ring in 4 variables, and we give it a grading that comes from this Chow group n-1 of P1 cross P1, which we computed in a previous example, and we got Z2. But now we need to remember more than the answer. We need to remember that it's not just Z2, but we need to remember the map in that exact sequence. What was the map? That was the given class of something. In the middle of that exact sequence was the direct sum of Z di. And that maps to the class group. We need to remember that beta map over there. It is over here. I brought it back from that slide. So degree of this monomial, by definition, was degree of this guy. Beta map is degree. It's take class. Beta is take class in an-1. That's what beta does. And that's precisely what goes in our definition of degree. And beta, if you go and look back at that example, was exactly this. But then now we can look for a second what that gives us. When are 2 of these in the same degree? When are 2 of these monomials in the same degree? Well, they are in the same degree if you add the exponents of x1 and x2, and separately you are and get the same, and then you add the exponents of x3 and x4 and you get the same. Then we just identify something that you have seen before, possibly you have seen before, a polynomial ring in 2 sets of variables that is homogeneous on each of the sets of variables. So that is what the Cox ring of this one is. Very good. And more generally, we could have repeated this exact argument for Pn cross Pm. We know the fans of these 2 guys, and we can produce the sequence that we did before for P1 cross P1. We can reproduce that, and then following this example in that case would give us the following answer. The same thing, but not just sets of variables of size 2. It would be of size n+1 here and m+1 here. The answer would be that the Cox ring for this guy would be a polynomial ring in 2 sets of variables, basically variables corresponding to this guy and to this guy, and the polynomials over there, the grading is that something is on the same degree if it's homogeneous, if it is homogeneous separately in the variables. In other words, the grading is a grading on Z2, and is by adding these ones over the exponents of these ones, and separately adding the exponents of these ones. Very good. Lastly, over here, if we look at this one, we already worked out the exact sequence computing the class group of this guy. The primitive generators of the arrays, we have had this notation, are the VIs, which are classes of the canonical vectors E sub i's. In the fan that we wrote for this one, for weighted projective space, there are exactly n+1 rays. Then we have a correspondence with exactly n+1 invariant divisors. When we want to write down the Cox ring, we get exactly n+1 variables. And the degree is something I was pointing out to you before. The sequence came from dot product with the vector q0 to qn, and the di's correspond to the canonical vector E sub I. So when you do dot product, you get qi. The degree of xi is qi. So then, what would be the Cox ring of this guy is the polynomial ring in n+1 variables when you, and with the following grading. The degree of the variable x0 is q0. The degree of the variable x1 is q1. The degree of the variable xn is qn. Very good. And then how are we going to use this ring attached to the variety? So we start with a variety, and we are attaching some, it's not just a ring, it's a C algebra. How are we going to use this C algebra? Well, the claim is that now it would allow us to generalize the construction of projective space as Cn+1 minus 0 mod C star. We are going to be able to generalize that to toric varieties. So this ring is the one that will play the role of the polynomial ring in n+1 variables in the case of projective space. But now we need an analog of the irrelevant ideal. This is how it arises. So we need an analog of the irrelevant ideal. The irrelevant ideal in the case of projective space is this one. In our case, what we are going to do is the following. For each cone, we are going to define a monomial. This is the notation for the monomial. And what is that monomial? You are going to multiply the variables for all rays not in that cone. So if we were in a picture like this, and these are my cones, and my picture was like V1, V2 was over here, V3 was over here, V4 over here, with corresponding divisors D1, D2, no, that one is not there, D2, D3, and D4, and with corresponding variables X1, X2, X3, and X4. Then what this is saying is that, for example, if I look at, say, let me get a new color over here with, say, for example, green. If I look at this cone, it will be multiplying the cones that are not, the rays that are not contained in that one. So I multiply this one, and this one. So I will get x1 times x2, not x1. x1 is contained. x2, x3, x4. Very good. And I'm going to try to draw in a different color. If the cone that I take was this one over here, then I will be multiplying only these ones. These are the rays that are not contained. This is x2 and this is x4. So for this cone sigma, the monomial x sigma with this hat would be x2 times x4. Very good. And let's take the ideal generated by these guys. And that one we are going to call the irrelevant ideal in this context for the toric variety x delta, x sigma, I'm sorry. I always say, many times I must have said x delta because for me, I always usually call them delta. Anyway, sigma is also very common. And let's go back to the example we started from. If your sigma is the fan that gives Pn, what is the irrelevant ideal in that case? We claim that you get the irrelevant ideal that is usually defined. And that's not so bad to see. Let's see in the case of P2. In the case of P2, but all of them work the same, what happens is that the cones start from a collection of n+1 vectors, the canonical vectors, and minus the sum of the canonical vectors, and the cones arise by taking proper collections of them. So if I look at the maximal cones, they are generated by n of the vectors, and then there is only one outside. So for each single variable, I can put all the other ones together, they span a cone, and if I use that cone, and I use this definition of the corresponding monomial, I get the variable that I started from. What I said is each variable is in here. It's just because you have n plus 1 rays, and any n of them span a cone. So you take one of them, the other n give you a cone, do x, that sigma hat gives you precisely the one that you isolated. Then this is true. Very nice. Then quotient construction. We can get our variety. Okay, let's see how. Well, with some assumptions. You will see the theorem in a second. Let's start from a toric variety. And the idea is that we are going to try to get it a quotient of this. It's going to be affine space of dimension the number of rays. And we are going to remove the zero set of the irrelevant ideal. Just like in the case of constructing a Pn, you started with Cn plus 1, removed 0, and then there was a quotient by some group that in that case was C star. Over here, the group is going to be the following. The group is this, but let's see why that's the one that we want to consider. Let's look at this exact sequence that we established before. We outline why it is true. So we have this exact sequence, and let's take home to C star. Then you get 1 over here, you get, by definition, this is G. So that's where the G came from. G is what you get by taking home of this one to C star. So it seems weird at this moment, but this is where it comes from. In the middle, you get, this is Z plus Z plus Z, as many copies as the number of rays. So when we take home to C star, we get as many copies of C star as the number of rays. And over here, one can do a little algebra to see what you get is the torus, the same torus that we have been working with. And then we notice the following. If we take affine space of this size, if we take affine space of this notation is like functions from here to here, but that's a vector space of size as many as the cardinality of the set. So it's the one that we really want to consider. Inside that one, we have this C star as many copies as the number of rays. This is a torus that acts on this affine space, and this exact sequence gives you an inclusion of G on this one. So then there is an action of G on this one. You see? This one, let me say, this torus is just the points in affine space with all coordinates different from 0. That's a group that acts by multiplication coordinate-wise in this space. And we have included G here, so G acts in this space. Now we notice that the action comes by multiplication with elements that are different from 0, complex numbers different from 0 in each entry. And then we analyze our V's of B, like this 0 set of the irrelevant ideal. It consists of coordinate spaces because we just define this by like monomials. It's a union of some linear subspaces over there that are coordinate. That is fixed under an action of C star to a power. Then we still have an action after we remove G acts on this set just by the inclusion of G here. But what we are saying is that since the 0 set of the irrelevant ideal is invariant, we get an action minus the 0 set of the irrelevant ideal. We have an action of G there. Then the claim is that that works nicely. For that action that we just described, if we have a toric variety and we assume the following, assume that the rays span in R. Assume that the rays span in R. In particular, the sequence from before now is fully exact. Like before we wrote 4 terms, we also now get the zero, get the injectivity on the left in a sequence that we wrote before. There are here, please, do you have a question? Oh, yes, certainly. Is there a question over there? Yes, please.
Yes. I don't know if it's an easy question. This is issue 3.4. Nothing. What would in general obviously mean that it is subjective? In terms of because TN is essentially intuitively is start to the power. What does it mean that it is subjective?
What would it mean for it to be surjective? Yes. Maybe we can talk about this in one moment. I don't know if I have a good answer to that. But I think it with the assumptions of the theorem, I think that one becomes surjective. And you get, maybe we can talk and see like what it means for it to be surjective. Maybe you can maybe explain what type of answer you are expecting to see if I wouldn't know. Yeah, if you tell me what type of answer you are expecting for that, like I mean, like what objects do you want to put assumptions on? If it is on the fan or on the, and then we can see what we can say. Very good. Like, is your question like what assumptions can we put maybe on the fan to get surjectivity here? I think the ones in the theorem are enough for that, and I don't know if I don't know. I would have to. We can think together other sets of assumptions that would grant you surjectivity here. I think the ones of the theorem are enough for that. Then what will happen over here is that with no more assumptions than this, just that your set of rays spans NR, then this is a categorical quotient and even after base change. So if you want, ignore this one for a second, it is a categorical quotient in the sense that when you have these other varieties with an action that map to your variety, then there is a factorization. It's like a certain universal property. It satisfies the universal property of quotients, and this is the part of categorical quotient, and the universal is basically it satisfies the same after some base change. And so this is a very nice result that you recover this one as a quotient, but that one might still have some issues because the points of the quotient might not be parameterizing orbits. Then there is this other notion that is stronger, a geometric quotient. In that one, additionally, like you have this map that you call a geometric quotient. It satisfies, locally you have a cover where you are basically taking the spec of the invariant rings, but additionally, each fiber is one orbit. And additionally, the topology is precisely the quotient topology. So something is open if and only if pi is the quotient map, pi inverse is open. So it's a couple of extra assumptions that one puts on a quotient to make it look nice, but like informally, is just you really want a parameter space for the orbits. That one calls a geometric quotient, and you get that if and only if your fan is simplicial. So if your cones are spanned by linearly independent vectors, you have a very nice quotient construction. And if it is not spanned by linearly independent vectors, you will still get some quotient construction. Not as nice, but you still get that. And this one would be really nice because, in particular, the elements down here, after you take the quotient, correspond to orbits in the original one. And what I'm saying is written over here. The geometric quotient part mentioned in 2 is the analog in algebraic geometry of the idea of a quotient under a group action, and the elements in the quotient correspond to orbits. That's part of the definition of geometric quotient, and is this other thing that I told you, that the quotient has the quotient topology, and then how you locally have discovered where you recover the patches below by taking invariance on the patches above, and then take this spec construction. And this other one, we are not saying much here, is what I was telling you about satisfying a certain universal property, and then stably, meaning by base change as well. But in the case of an affine variety, we point out that you get it this way. Okay, so under the hypothesis of the theorem, notice that you can get your toric varieties this way then. You get your toric variety by, say that you start from your fan, that the rays fan in R. So a different construction of your toric variety is this object you can have. Yes, just from the fan, you have a vector space with as dimension the number of rays. You can write down your irrelevant ideal from the fan. You can remove your irrelevant ideal from there in this affine space. There is an action of G, which G we can compute, because we can compute AN minus 1, and then we just do home to C star, and then that quotient is an alternative construction of your toric variety, without passing to these fans and the semigroups and all of that we did. This also gives you X sigma. Very good. I think we are fine. And then, yes, please. Going back.
Yeah. In the case that sigma is just a single cone, so the affine case, is number one correct even without removing the locus of the irrelevant ideal?
You are right, because like it's a very good point. Say Jack is proposing, let's take the following fan. The fan is all the faces of a given cone, a cone with all its faces. So in that case, let's think for a moment what our B, capital B is. Our irrelevant ideal goes as follows, like you take some cone and you do product of all the variables that are not in that cone, but that runs over all the cones, in particular over the whole thing, in which case we don't miss anything. So the irrelevant ideal contains, in that case, is like the element 1. So this irrelevant ideal is like the whole thing, so the zero set would be nothing. So it's an excellent point in that case. When you do it for one cone, you don't need to remove anything. Very good. Thanks a lot for pointing that out. Before giving some examples over here, let's say, how do you compute these two guys? Is by reading off from the exact sequences that we have written before. So if you call your first lattice element on the rays by V with the same sub-index, meaning for the ray rho, the first lattice point is called V sub rho. If the rays are rho 1 to rho s, then the primitive elements in those rays are V sub rho 1 to V sub rho s, and we define a primitive collection as follows. This is a set of some of those VIs that they do not lie in a cone, but every proper subset does lie in a cone. We can write some examples of that in one moment. Then one can see that the irrelevant ideal goes like this. The irrelevant ideal is the union of the zero sets over those primitive collections. In case all of this is like seeming too weird, my impression, my 2 cents here to make this less confusing is, say that we look at the case of P1 cross P1. This is what is kind of happening in the background. That one has a fan like this, with 4 cones like this, but this lives in R2. So now we are going to put that picture in R4. So we are going to go to R4, and we put as many rays as the dimension. No, that's the dimension. As many, like the dimension, yes, like the other way around. We take the dimension as the number of rays. What I said was correct, but like it's not in that direction. like is that we take the dimension as the number of rays. So we have a, pretend that those 4 are linearly independent and that those 4 are these, correspond to these 4, right? So this is a picture in R4. What is happening is that I start with that R4 and pretend that I start with the first octant thing, whatever it's called in 4 dimensions. And what the relevant ideal should be removing is that removing some cones in such a way that you get like a new fan that is like these guys over here. With this part in front, kind of like a hole. Like a hole here. So it's like if I somehow take this same original fan and I am placing it over there, I think that's what is happening. That's what this thing does. Then in a certain sense, it makes it less surprising that out of this picture, you get this one as a quotient. Because it's like if you somehow manage a way to include this one now in R4. And it sits now weirdly. It was flat before, now it sits kind of weirdly over there. But now it makes it not surprising that, oh, then yeah, this could be like a quotient of that. Anyway, then now I'm just saying here, hey, there is this terminology of Varieties that these primitive collections allow you to see what it is happening over here, what the zero set of your irrelevant ideal is. So to clarify, this that I drew over here is not the zero set of the irrelevant ideal. It's not that I was working on the affine space. So this is R4 because we are working over the complex numbers. This is R4, so here I'm looking at some fan. And what I'm saying is that it's like if I place this one in R4. Like using these instructions that you take these ones linearly independent, that produces my R4, and I somehow put this fan over there, and it's the natural way. Now, what is the G? G is the kernel of, it can be seen as the kernel of some map before. Like if we go back to one of these sequences, we see it as the kernel of some map, and the map over there we understand. So one can see it's exactly this. If you look at the G inside like C, a copy of C star to as many as the rays, or C as many as the number of rays, the map over there mapping to 0 means exactly this. And then an observation is, well, this is for all m in M, but it is enough to do it over a Z basis. Because if it is true that you have this equation over a Z basis, then for any other M, it would be a product of the relations over the Z basis, and a product of ones is 1. So this gives you a way to compute G. It was like a bit fast, but let's make it a little bit more concrete in some example over here. Just again, let's go back to the one that we have been looking at. P1 cross P1. What is the construction in this case? One can check that the irrelevant ideal in the case of P1 cross P1 is this. Let's try to see that quickly. We have cones like this for P1 cross P1, and we have variables with these names, x1, x2, x3, and x4. So when we work with this cone, is the product of the variables corresponding to rays that are not there. So it's the product of these two. So x2, x4. The one requires that one. And you see that as you go over the 4 big cones, it gives you these other 4. It's basically products of the variables that are not in each of the cones. So for one of them, I get the product of these 2. For the one over here, I get the product of these 2. For the one over here, I get the product of these 2, and so on. It gives me the exact 4. And now you can see that if you take smaller dimensional cones, then I don't get anything new, because it would be a product of even more things than if I had taken a larger cone. One can see that even though we gave the definition of capital B ranging over all cones, it's enough to do it over maximal cones if you order your cones partially by inclusion. You just need to be the largest ones, because if you take a smaller one, then you get a product of even more X rows, but then product of fewer of them generates the other one as ideal. So you are fine. Then, yes, these guys are not lying over here. This is mean us, I guess. We're not lying. So if we now look at this one, separating as two copies, it makes sense. Like this is just C4, but let's for convenience put the two sets of variables separately. We see that this is the irrelevant ideal using these primitive collections because there are two of them exactly. The primitive collections, let me go back a little bit here and write down some of those. What are collections of vectors that are not in a cone, but any proper set is? We can think for a second and realize that these two guys are one of them, and these two guys together are another one of them. So then we see that the irrelevant ideal, the zero set, is the union of the zero set of those guys, which is 0 cross C2 and C2 cross 0. We compute G using what was in the previous slide. What you need is tuples like this that satisfies these products equal to 1. But in this case, using the EIs that we see over here, we get exactly these relations. So G is the collection of mu lambdas that, since you have these things equal to 1, I have mu and mu here, lambda and lambda here. And then the quotient that the theorem claims would be like this, that we have C2 cross C2, we set that over here, and we remove the zero set of the irrelevant ideal. You see that one over here. And the action is by G acting this way. This G acting this way. But then if you see what is happening, we are scaling this one by lambda after removing this. That gives me like a P1 over there. And I am here removing this and scaling by lambda. Like in the first copy, I scale by mu any way I like. In the second copy, I scale by lambda any way I like. So this is just the usual construction of P1 cross P1. Then now we see how the crossing construction works. And since it is 11 a.m., then it's a great time to stop. Thanks a lot for your attention.